About module 3, that is combinational logic circuit, right? So in today's class we are going to study how we can do the designing with limited fanning, and then we'll study what is the significance of delays, gate delays, right? So before we proceed further, we'll continue with where we have stopped in the previous class. I hope you understood how we can draw the two-level NAND circuit for the given expression, first by drawing the AND/OR circuit and then converting it into two-level NAND. So what you need to do is first simplify the expression, then get the AND/OR circuit using AND and OR gates. Then as it is, replace every gate by NAND gate and retain the interconnection as it is. Show all the inputs as it is, except if there is any single literal input present for the output gate, that particular input should be complemented. That is what is procedure you need to follow when you are drawing a two-level NAND circuit for two-level AND/OR circuit. The same procedure you need to use for two-level NOR circuit also. Again, what you need to do there is, first you have to get the simplified expression using K-map or any other technique. Then you need to draw the circuit again using AND and OR gates, and then replace every AND and OR gate by a NOR gate. Retain all the interconnection as it is, retain all the inputs also as it is, except for the output gate. If there is any single input, that input should be given in complemented form. That is the procedure you need to use for drawing any two-level NAND circuit or two-level NOR circuit. And already we have discussed about what exactly you mean by level of a combinational logic circuit, right? So we'll take one important example now, and we'll see how we can realize multiple output functions with limited like fanning. They may give that there is a limited fanning given, then how we can simplify those expressions. Independent expressions will be given to you, how we can simplify those independent equations, and then together we want to implement them, how it can be done, right? So all of you take down this next example. This is an important example. We'll see how we can solve this particular example. Just take down this. Hope the screen is visible. Only take down that example. That is, can anybody read the example there? Yes? Realize? Yes, someone can read it. Can someone read? Yes?
Realize the following functions using only two input NAND gates and inverters.
Okay. The functions are F1 equal to sigma m 0, 2, 3, 4, 5, F2 equal to sigma m 0, 2, 3, 4, 7, and F3 equal to sigma m 1, 2, 6, 7. Three functions are given, right? Now we need to simplify these three functions, get the individual simplified expressions, and then we'll see how we can modify those expressions and we can implement the same with whatever the restriction they have put. Here you have to use what? Two input NAND gates only, right? Anyhow, inverted inputs are available, so we need not bother about the inverters. So we'll assume that the inverted or complemented inputs are also available. So quickly, can you simplify these three functions using K-map? How many variable K-maps you have to use now? How many variable K-map you need to use?
Three variables.
Three variable K-map for F1, F2 as well as F3. Fine. So quickly, all of you simplify it and tell me the answer. What is the answer you will be getting for F1? What answer you are going to get for F2, and what will be the answer for F3? Anybody got the answer? Have you taken down the example? All of you? Yes? There should be reply from your end. Either at least say yes or no. All of you have taken down that example or no?
Yes, sir.
Yeah. Now simplify using three variable K-map. Three variable K-maps you have to write and get the simplified expression for F1, F2 and F3. Get it fast. What are the simplified expressions for F1, F2 and F3?
Sir, F1 answer.
F1, F2 and F3. What is the answer for F1 you are getting?
A bar C bar plus A bar B plus AB bar.
A bar, C bar for F1. Just check. You can see here three variable K-map you have to draw. A, B, C I have taken as the inputs. Right, sigma m 0, 2, 3, 4, 5, 0, 2, 3, 4, 5. So we'll get here three different pairs. You can see this is one pair, then this is second pair, and this will be the third pair. So what is the answer you are getting, Adnan? Yes?
1 minute. Huh?
Here the answers are there on the screen. You can just check that.
Sir.
Yes.
B bar C.
B bar C bar.
C. Sorry. B bar C bar.
Okay.
C bar. And A bar C.
And
A bar C.
A bar C.
Yes, sir.
How A bar C?
Sir, if we combine 0 and 2, sir.
0 and 2.
Adjacent.
Okay. But anyhow, here independent is possible. You write like this only. Right? Why 0 and 2? If you combine 0 and 2, then this again you have to make one more, no? One extra group you will be making in that case. Right?
Yes, sir.
So you should not combine 0 and 2. If you combine 0 and 2, what is happening is again you are doing this 2, you are clubbing with this as well as this, which is not required actually, because both the cell number 3 and 2 are independently covered in one pair. Then why you want to combine them again in a pair with cell 0 and 2? That should not be done, right? So the answer what you have got, all of you should got this particular answer. You should have got this answer. F1 equal to A B bar plus A bar B plus B bar C bar. All of you got this? Yes?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Then similarly check the second answer. Second also all of you got this? B bar C bar plus
Yes, sir.
A bar B plus BC.
Yes,
Is
sir.
that clear?
Yes, sir.
And third one what you got? What is the third one?
A bar B bar C plus AB plus BC bar.
Plus BC bar. Okay. I hope all of you have got these three answers. Everybody has got these three answers. Yes. First one you got B bar C bar plus A B bar plus A bar B. Then second one you got B bar C bar plus BC plus A bar B. And third one you got A bar B bar C plus AB plus BC bar. Is that clear? Now, if you observe these three functions, how they can be implemented, like what is the hardware required to implement these? we need each function requires 3 input OR gate because it is a sum of 3 product terms. You can see here 1, 2, 3. Here also we have 1, 2, 3, 1, 2, 3. So we need 3 input OR gate, right? So when you want to 3 input OR gate again, then accordingly you may need 3 input NAND or NOR gate also. So it is not possible to implement this function F1 or F2 or F3 as it is because they have asked us to design these circuits or implement these functions using what? Using what? You have to implement these functions using only 2 input. What? Yes,
NAND
what is
gate.
the question?
NAND gates.
2 input NAND gates. And if required, you can use the inverter. And that is what is the constraint given in this. So it is not possible to implement these functions as it is. So what we do? When you want to use the limited fan in, what is the procedure I have told or the thumb rule I have told? What you need to do? You need to, yes, Chandan, what you need to do?
Factorize.
Yes, you have to factorize the expression, simplified expressions, what you got. Normally, K-map gives you simplified expression. Directly, you can implement it using the required gates. But since there is a restriction or constraint that you have to use a particular gate only and particular fan-in gate only. So here, what is the fan-in they have mentioned? 2. That is, you have a NAND gate which can handle only 2 inputs. So you can't have more than 2 inputs. So obviously we need to factorize. So how we can do the factorization? So you can see the factorization in the first expression. What we can do is between first and second term, we can take B bar common. If I take this B bar common, here left is C bar and here it is A. So I can write it as B bar into bracket A plus C bar. And the third term is kept as it is. Now this can be implemented by using 1 2 input gate. This term can be implemented by using 1 2 input gate and then again AND operation. So we don't have anywhere more than 2 terms coming. This is 1 term, then you are taking AND operation with this. So whatever term you will be getting, this and this, you will be ORing. So everywhere we have only 2 terms. So definitely it can be implemented using only 2 input gates. Right? Similarly, in the second expression, if you see it, again I can take here B common between these two. If I take B common, it becomes B into A bar plus C plus B bar C bar. Right? This is correct. This is what we get simplification after taking B common between these two. But whenever you are implementing multi-output functions, you should see that you will get similar terms in different equations so that you can use optimized hardware, right? You can see here in the first equation we have the term A plus C bar or A bar B. So try to get either this term or this term in second also. So what we can do is we have a term here B bar C bar, right, plus BC. So this B bar C bar plus BC, what I want to do is, since A bar B is there in the first equation and in the second, I want to retain that as it is. So to retain this, you need to do B bar C bar plus BC can be written as B bar plus C into B plus C bar, right? B bar C bar plus BC can be written as B bar plus C into B plus C bar. Then you may ask how? You just multiply this. B bar B cancel, then C bar is cancelled. So you get B bar, C bar and CB. B bar, C bar and CB or BC. So B bar, C bar plus BC is equivalent to B bar plus C and B plus C bar. So I will take this expression, then I will take this. Then in the third, what we can do is, you can see the third equation. Here I have a B C bar term, here I have A B term, but here there are 3 terms. So I can't implement a product of 3 literals using 2 input NAND gate. So how we can split this? So this A bar, B bar, C, which is there, what we do is, I will write this as A bar into bracket B bar C. If you write A bar into bracket B bar C, right, Then that B bar C, if you use a De Morgan's theorem, it can be written as B plus C bar, its whole bar. So I can write that A bar B bar C as what? A bar B bar C can be written as what I have written it as? A bar, then and that with B bar and C. So I have this equation, and the third equation is this itself. This is the third equation wherein this three term product is split into two. Now this F1, F2, F3 we have to implement. So how we can implement this F1, F2, F3? So you can see here, this is the simple logic. Whatever the circuit is given as it is, I have drawn that simplified equations using what? And or an inverter. I have used OR gate, I have used AND gate, I have used another OR gate, and whatever the expression we have got, you can see here, F1 is what? B bar and A plus C bar or A bar B, right? Similarly, F2 equal to this, F3 equal to this. This is the normal circuit using AND OR gate, right? Now this you need to translate is into NAND gate, and I told how to do this NAND gate. Replace every gate by a NAND gate except the inverter, because they asked you can use the inverter also. So this inverter is retained as it is. Then these three gates are replaced by three NAND gates. These 5 gates are replaced by 5 NAND gates here, and these 3 OR gates are also replaced by this, right? And then the inputs are given accordingly, right? You can see here whatever the term we have got. Since we want here A plus C bar, you can see here A and C bar was there. Here what is given? A bar and C, because you want OR operation, and or NAND gives a dot operation, so you have to give the inputs in complemented form, right? So here also the inputs are given in complemented form. Here these inputs are also given in complemented form, but these should be written as it is here, because AND you are replacing it to NAND, two NANDs, so automatically that 2 NAND of NAND is AND only, right? So this is how you have to design a circuit with limited gate fan in, right? I hope all of you understood this. You need to solve this example. Whatever the example is shown there, you have to simplify each and every expression independently using independent K-map. Then whatever the expressions you have got, all those expressions try to simplify or factorize in such a way that you should have a similar or common terms, so that you can be in the need of less hardware, right? So once you get that simplified expression, you can draw the circuit using AND or NOT gates like this, and then translate that circuit into a NAND gate circuit, like you can use the multi-level technique of implementing the Boolean equation or the combinational circuit. Is this clear? All of you understood this? Yes? All of you understood this or no? Tell either yes or no, whether you understood this or no. Okay? This was the same circuit. Easily you can draw that. I hope it is clear. All of you understood? Okay. Unless and until you practice it, you will not get that feel. So compulsory, you need to practice it. Then only you will be able to like simplify such expression and draw the logic diagram for the same. Fine. Okay, we'll proceed further. We'll go to the next part of this module. First part is just drawing the circuits with limited fan-in. Briefly, I have explained that. You just go through. I will be sharing this content with you. You can go through the slides, PDF, and if you have any queries, you can get back to me. Okay. Now we'll go to the next part. What exactly you mean by gate delays and timing diagrams? Right. So far, whatever the gates we have used, we assume that they don't have any propagation delay. So the moment input changes, the output should change. But in reality, it doesn't happen. Right? Whenever the inputs to the logic gates are changed, the output should change instantaneously. But in reality, this doesn't happen because all these gates, what we have studied, they use switching elements like transistors or the FETs. And since the gate in turn uses switching elements like transistors or FETs, these switching devices, they need certain finite time to react to the change in the input so that the change in the gate output is reflected, and this change in the gate output is delayed with respect to input change, and this delay itself is called as propagation delay of the gate. So what exactly you mean by propagation delay of the gate? Right. So the moment you give the inputs to the gate, the output also should be obtained instantaneously. But practically it doesn't happen because of the switching elements used in the gates. So whenever the inputs are changed, the output will be available after some delay, and that delay, the gate delay, is called as propagation delay. And the major reason for this propagation delay is the switching elements used in the gate circuits. So the amount of time required for a gate to change the output when inputs are changed, that delay is called as propagation delay. I hope the definition of propagation delay is clear. Can anybody define what is propagation delay? Yes, Akash, can you define what is propagation delay? Yes, Akash Desai, you are there? Yes, anybody else can define what is propagation delay? Yes,
Time taken for signal to reach its destination.
time taken by signal
To reach its destination.
to reach its destination. That's not correct definition. I'm asking what is propagation delay of a gate. Whenever you have a logic gate, every logic gate will have a propagation delay because of the switching elements. So I want what is the definition of propagation delay of the gate, right? Yes, Sohan.
Yes, sir.
Yes, what is propagation delay?
So I guess it's the time taken to, I mean, the delay or else the time required to show the output when the input is changed. When the
Input is changed. Okay. Whenever you apply the inputs to the gate, output of the gate immediately it will not change. When the inputs are applied, after some time, outputs will be changed or outputs are reflected. So this delay between the appearance of the input and the appearance of the output or available of the output is called as propagation delay of the gate. And because of this propagation delay of the gate, the glitches occur in the circuits, in the logic circuit or in the combinational circuits. Right? So we'll see how to take care of these gate delays or the propagation delays. Right? So this concept of propagation delay will be more clear with this slide. What you can see in this slide? Which gate I have shown there? I have shown one simple gate there. And what is that gate? Yes? What is
Not
the
gate.
gate here? This is the NOT gate
No.
or the inverter. Assume that this inverter has a small propagation delay of, say, this epsilon. Epsilon is the propagation delay of this particular gate. Right? Normally, what happens? X is the input, X bar is the output. Now, here for this interval, what is the input for the first interval? Here, for this interval, what is the input? What is the input x for this interval? What is the value here of the input? Yes? What is this value of the input? 0. This is 1. This is 0. So if you have the ideal gate with 0 propagation delay, what output we are expected? Whenever input is 0, output should be 1. And whenever input is 1, output should be 0. And whenever again the input is 0, output should be 1. This is what is that red color waveform which I have drawn is the expected waveform. But here, the gate which we have assumed has a propagation delay of epsilon. So what it does, right? So outputs will be delayed by epsilon. So you consider this as the time interval now. So at this interval, input is changing from 0 to 1. Output also should change from 1 to 0 instantaneously. But the output will not change from 1 to 0 instantaneously. It remains 1 for a certain time and then it becomes 0. So this is called as what? What is this interval is called as? This interval is called as the propagation delay. You can see actually the output also should change here only, but the output is not changing here. It is changing at this particular interval, which is after epsilon 1 from the input changes. So this epsilon 1 is called as the propagation delay of the gate. Now the input remains 1. So here the input is changing to 0. So output should change from 0 to 1 instantaneously at this instant only. But it will not change at this instant. It changed after some delay, that is epsilon 2, and this epsilon 2 is called as the gate delay or the propagation delay of the gate. So I hope it is clear how to draw these. These are called as timing diagrams in fact. Whatever I have drawn is the timing diagram. This is ideal timing diagram. We should get like this. Right, but practical timing diagram, you can see there is certain delay when the input changes. Output is not changing immediately. Output is changing after some time. Hence, this is called as the propagation delay of the gate. And this diagram, wherein we have shown the input and output along the time scale, how the inputs and outputs are changing with respect to time. And this particular diagram, what we get is called as what it is called as timing diagram of the circuit or timing diagram of this particular gate. I hope the concept of gate delay or propagation delay and timing diagram is clear. All of you understood this?
Yes, sir.
Is it clear? Propagation delay, what happens? Yes, how you get the propagation delay, I have explained you because of the switching elements. And what happens when there is a propagation delay? If there is a propagation delay with the gate, output will not change immediately. Output will change after some time, and that some time after which the output changes is called as the propagation delay of the gate. Is it fine? So these timing diagrams are nothing but the timing diagrams are frequently used in the analysis of sequential circuit with respect to time, like the flip-flops, latches, RAM, memory, etc. What these timing diagrams basically show? These timing diagrams show various signals in the circuit as a function of time. How the signals are changing with respect to time, that is indicated in the timing diagram. Several variables are usually plotted with the same time scale so that the times at which these variables change with respect to each other can easily be observed. That means, suppose if you draw a time axis, I can draw different waveforms here. Say this is one waveform A, I'll draw another waveform, right, with respect to this time. So you can draw several waveforms, right? We can plot on the same time scale so that you can check where actually which input is changing and how that will be having an effect in the output. So to see the effect of change in the input on the output, this timing diagram plays a very important role, and also you can clearly understand the concept of propagation delay or gate delays of the gates used in the design of combinational circuit. So one more example is given. All of you try to analyze this. One simple example is given here. What the circuit consists of? Gate 1 is which gate? There are two gates shown, gate 1 and gate 2. The output of first gate we have denoted by gate 1. Output of second gate is denoted by gate 2, that is G2. Gate 1 is which gate? Gate 1 is AND gate, and gate 2 is
And gate.
NOR gate. NOR gate. Right. Now you can see there, at time t equal to 0, they have given the input A is 0 and C is 0. Right. And if B changes from 0 to 1, like how we can draw the output waveform, that is what is shown here. And here we are assuming that every gate is having a propagation delay of 20 nanoseconds. Now when I say propagation delay of 20 nanoseconds, what it means? Each gate is assumed to have a delay of 20 nanoseconds. Means whenever inputs are changed, output will change after what? 20 nanoseconds. And since in this circuit, output of first gate is given as the input to the next gate, suppose whenever input A changes, at a particular time interval, say t equal to 0, when the output G1 will change? When the output G1 will change after a delay of 20 nanoseconds. And similarly, output G2 will change after a delay of what? Another 20 nanoseconds, that is 40 nanoseconds. That means here every gate is having a propagation delay of 20 nanoseconds. So how this timing diagram is drawn? Now you can see here we are assuming B equal to 1 and C equal to 0. B and C inputs are fixed, right? That's why here B and C inputs are not shown. In fact, if you want to draw, you have to draw here like B is 1 and C is 0. Say this is B, this is C. B is equal to 1 throughout, C is equal to 0 throughout, right? They are fixed. But at time t equal to 40, here A is changing from 0 to 1. This is 0, 1, right? 0. So input A is changing from 0 to 1. At what time? What time it is changing? See here, what is that time? At 40 nanosecond, input A is changing from 0 to 1. So at 40 nanosecond, you have made A is equal to 1. So already B is 1. Now you have made A equal to 1. G should be how much? Because it is an AND gate. G also should be what? 1. So when you will get G equal to 1? At 40 itself, because A has become 1 at 40 nanosecond. A had changed to 1 at 40 nanosecond. So G also should change at 40 nanoseconds. Yes or no? G also should change at 40 nanoseconds because A had changed from 0 to 1 at 40. But it will not change at 40. Why? Why it will not change at 40? Because this gate has a propagation delay of how much? This gate has a propagation delay of 20 nanoseconds. So the output G, instead of becoming 1 at 40 itself, when it becomes 1, you can see here, when it becomes 1, after 20 nanoseconds. So 40 input had changed. So you add this 20 to that. So at 60 nanoseconds, the output G1 will become 1. And it remains 1 for how much time? As long as the input A is 1, right? G1 should be 1. So here again, the input A has become 0. At what time it has become 0? 100. So 100 it should go to 0. Output of G1 should go to 0 at 100, but it will not go at 100 because this delay of 20 nanosecond will again come here. And the output G1 will become 0 when it becomes 0 at 120. Though the input had changed again at 100, output is changing at 120. So at 120, G1 becomes 0 and it remains 0. This is how the output G1 gets. Now, when G1 has changed, when G1 is changing, G1 is changing from 0 to 1 at 60 nanosecond. So this is becoming 1. C is 0. 1 or 0 is 1 complement. So it should become 0. So when G2 should become 0 now. This had changed at 60. At 60, G1 had changed from 0 to 1. So at 60 itself, G2 should become 0. But at 60, G2 will not become 0. When the G2 will become 0, to this you have to add another delay of 20, because this gate is also having a delay of 20. So at 80 nanosecond, G2 will become 0. You can see here. At 80 nanosecond, G2 will become 0. And then from 80 to 140, it remains 0. Why till 140? Because at 120, input G1 had changed. So to that, you have to add another 20. And at 140, it should become 1. So this is how the gate delay will have effect on the timing diagram of a particular circuit. I hope it is clear. All of you understood? This particular simple example I have taken, and we have assumed here every gate is having a propagation delay of 20. So that propagation delay, how it is having effect on the timing diagram is illustrated in this particular example. Any doubts here? All of you understood? Yes?
Yes, sir.
Okay, very good. Right. So there one more example is given. You can just try to analyze this particular example. This is a simple example again. What we have shown here is figure shows a timing diagram for a circuit with an added delay of the element. Here what we are assuming is gates are having their own delay, and we have added one more delay element, that is X we have given directly to the input, and X we are delaying by 1 microsecond, and then we are giving it to this same gate, and we are calling that output as Y. So the output Z should be X and Y because it is an AND gate, right? So what happens here? The input X consists of 2 pulses, the first of which is of 2 microseconds width, and the second is of 3 microseconds. Like I have taken one example here. Assume that X is having 2 pulses, one is of 2 microseconds here, another is of 3 microseconds. So if you assume that X is changing as per this, if X is changing as per this, you have to draw the timing diagram. And when you are drawing the timing diagram, right, you have to consider that 1 microsecond, the additional delay of 1 microsecond, right? So we'll see how do we get the output now. Initially, X is 0, so Y is also 0, we'll assume, and we'll assume that here the input is changing. This is our starting point now. Now here X has become 1. This is the rising edge. This is called as rising edge of the clock. This is called as falling edge of the clock. So rising edge, input X is changing from 0 to 1. So when X changes from 0 to 1 at 1 microseconds, when the Y will change? X has changed from 0 to 1 at 1 microsecond. So when Y will change? Y will change after a delay of how much? How much?
1 microsecond.
1 microsecond.
1 mic.
So there is a delay of 1 microsecond. So Y, you can see here, after a delay of 1 microsecond, whatever value X takes, same Y has to take, but it will not take immediately. It will take after a delay of this particular 1 microsecond. So Y becomes 1 at 2 microseconds, right? Now, at this particular interval, you can see what is happening. At X, like time t equal to 2 microsecond, your X is 1 and Y is also 1. So what should be the output Z? Both have become 1 at 2 microseconds. So at 2 microseconds, output Z should become what? When this is 1 and this is 1, output should be 1. But you can see again here, it will not become immediately 1. It will become 1 after some time, that is epsilon. And what is that epsilon? What is that epsilon?
Propagation delay.
It is the gate delay. I hope you are getting 1 microsecond is the delay element, whereas this gate will have its own delay epsilon. So Z also will be delayed by certain time, that is epsilon. Now this will remain high for 2 microseconds, then it goes low. This again remains high, then it goes low. Then again here you can see, right? X is becoming 1 at 6 microsecond, but there is a delay of 1 microsecond. So again, Y becomes high after a delay of 1 microseconds, and Z becomes high again after a delay of what? The epsilon, that is the gate delay. So here in this example, what I explained to you is, in addition to the propagation delay, if there is an added delay, how we should take care of that. That is what is explained here, and this particular timing diagram is drawn. Is that clear? All of you understood it? Yes, how we should draw the timing diagram? It is very simple concept of drawing the timing diagram, but when gate delays are involved, you have to be very careful in drawing the timing diagrams properly. Is it clear? All of you understood it? Fine? Shall we go ahead? Right, that's what whatever I have explained is given that here. Now, once we know about the delays in the gates, these delays we are getting in the gates because of what? Because of the switching elements involved in the gates. And because of the switching elements, we are getting propagation delay, and because of this propagation delays, output will not change instantaneously. That is what is shown in the timing diagrams. Now, what is the consequence of these gate delays, right? So, we come across the term called hazards in combinational logic. Now, we are going to discuss about what exactly you mean by hazards. When the input to a combinational circuit changes, right? Normally, output should change immediately without any transients. But many a time, when the input to a combinational circuit changes, unwanted switching transients may appear in the output, and these unwanted switching transients that we get in the output, they themselves are called as hazards in the combinational circuit. So, for example, in a particular circuit, I am expecting this kind of output, but because of the switching elements and the delays in the circuit, I may get the outputs like some glitches. We will get like this, right? So these glitches, what we get, these are called as hazards in the digital circuit or the combinational circuit. These transients occur when different paths from the input to output have different propagation delays. Say a particular input, you may travel to the output by different ways. Different elements you will be using. Here different gate, here you may have different gate. So every path may have different propagation delay associated with it, and that may lead to the transients in the circuit, and those transients are called as hazards in the digital circuit or the combinational circuit. And basically there are two types of hazards. Those are called as static hazard and dynamic hazards, right? So what exactly you mean by static hazard and dynamic hazards? That is, in response to any single input change and for some combination of propagation delays, a circuit output may momentarily go to 0 when it should remain to constant 1, right? Or otherwise also, if the output may momentarily go to 1 when it should remain at 0. And these kind of hazards are called as static hazard. That means the output has to remain either 0 or 1. But it may happen that where the output should remain 0, momentarily their output may go to 1, and where the output should remain 1, momentarily the output may go to 0. Such kinds of hazards are called as static hazard, and these static hazards are of two types: static 0 hazard and static 1 hazard. Now, what do you mean by static 1 hazard? Where the output should supposed to be 1, like output has to remain 1 throughout, but because of the glitches, because of the delays, momentarily the output will go to 0. Such type of hazard is called as static 1 hazard. It has to remain 1, but in between unwanted 0 output you are getting as a glitch. So such hazard is called as static 1 hazard. Static 1, in short, you have to remember what? Compulsory it has to remain 1, but momentarily it will go 0. That type of hazard is called as static 1 hazard. Then what do you mean by static 0? It is opposite of that. You can see here. What is static 0 hazard? The output should remain 0, but momentarily it is going 1 and then again it is coming 0. such kind of hazards are called as static zero hazard. So there are two different types of static hazards called static 1 hazard and static 0 hazard, right? Momentarily it goes to 0 or 1. So those are called as static. It is not permanent. Whereas it may happen that in some of the combinational circuit, when the output is supposed to change from 0 to 1 or from 1 to 0, the output may change 3 or more times. Then that circuit is said to have a dynamic hazard. That is, change is allowed, but there should be only one change. The output should change from 0 to 1 only. But instead of changing it only once from 0 to 1, it will again change from 1 to 0 and then again from 0 to 1. If instead of single change, if you observe multiple changes, then that type of hazard is called as dynamic hazard. It may be changing from 0 to 1 multiple times, or it may be changing from 1 to 0 multiple times. Then such kind of hazards are called as dynamic hazards. I hope the difference between dynamic hazard and static hazard is clear, and in particular what is static 0 hazard and static 1 hazard. Is that clear? Can anybody explain me what is static 1 hazard? Yes? Yes, Ujjwala, can you define what is static 1 hazard? Yes?
Yes, sir. The output
What is
is
static 1 hazard? Yes?
the output is momentarily 1 and
Static 0 hazard means what? The output should static 0 means output should remain at 0 only, but momentarily it will go to 1. That type of hazard is called as static 0 hazard. Then what is static 1 hazard? Static 1 hazard means what? The output should compulsorily remain 1, but momentarily it changes to 0. Then that is called as static 1 hazard. So you will be under the wrong impression that when I ask static 1, you will say that if the input output is momentarily changing 1, it is called as static 1, and if the output is momentarily changing 0, it is static 0. No, it is other way. Right? Is that clear? What do you mean by static 1 hazard and static 0 hazard? Then what is dynamic hazard? Sahil, can you define what is dynamic hazard?
Yes, sir. In dynamic hazards, the output continuously goes on changing, like from 1 to 0 or 0 to 1.
Okay. If the output, like actually the output should supposed to change only once from 0 to 1 or from 1 to 0, but you observe what? Multiple changes. If you observe multiple changes in the output, then that type of hazard is called as dynamic hazard. Is that clear? What do you mean by dynamic hazard and what do you mean by static hazard? Right? So what exactly are these static hazard and dynamic hazard? In detail, we'll study it in the next class. So if you have any difficulties here, you can ask before we stop the today's class. If you have any difficulties, you can